Hi everyone, my name is Caitlin Yang and I'll be walking you through tutorial 4, which will show you how to apply a trained model to generate predictions for a new set of compounds. In the previous tutorial, tutorial 3, we selected the best performing model for predicting values for inhibition of SLC6A3. Now we'll apply it to the test subset of compounds from the original training dataset. The actual values for these compounds are known, so we can evaluate performance by plotting the predicted values against the actual values. A higher R-squared value, with a slope close to 1, will indicate better model performance. Two key functions that will be used are the predict from model file and plot pred versus actual from df functions. After the test dataset is generated, the first function will take the path to the tarball file where the model is saved and predict pKi values for the new test set compounds. Then the prediction performance will be evaluated using the R-squared score. The second function will take a data frame containing both the predicted and actual values for the pKi and output a plot that visualizes the relationship between these values. This will allow us to evaluate the model's performance. Now let's run through this notebook. First, let's import the required libraries, pandas, numpy, matplotlib, and seaborn, to handle data and perform data visualizations. We'll also import the predict from model function for making predictions and R-squared score function to calculate the R-squared value, which is a metric for evaluating how well the model's predictions match the actual values. And now let's prepare the test dataset. Here we'll select the test data from the curated pre-featurized dataset. We start by defining file paths. Split file path points to the CSV file that contains the splitting information for the dataset, so which compounds are in the training, validation, and test datasets. The curated data path points to the curated dataset with RD-kit scale descriptors for the compounds. The descriptors being scaled means that they're scaled by molecule size. Both of these files are then read into pandas data frames. To identify the compound IDs of interest, we subset the split data frame to only include rows with the value of test under the subset column, because we're creating a test set. We use the unique method to extract the unique compound IDs. Then we only include the data from the curated data frame that corresponds to the test IDs of interest that we extracted in the previous line. The compound IDs that are in the test IDs we just defined are stored in a new data frame, test data. Now let's look at the beginning of the data frame with the most important columns. Here we can see the compound ID, SMILE string for the compound's molecular structure, and the average pKi for each compound in the test set. Now that we have our test set, let's use a pre-trained model to run predictions on compounds in that set. If the original model response column was average pKi, the return data frame will contain columns average pKi actual, which contains the actual values, average pKi pred, which contains the predicted values, and average pKi std, which contains standard deviations for the predictions. Also note that if you want to run a model that was trained on a different machine, you'll need to specify another parameter, external training data, which specifies the path to the local copy of the training dataset. And now let's run this cell. The model directory is defined, and this specifies the path to the pre-trained model, which is saved in a tarball file. If you recall tutorial 3, this is the model path that we saved at the very end of the tutorial for the selected model with the best performance. We're using the test data frame as our input, meaning that the compounds in this test set are the ones that we want the model to make predictions on. We're also specifying columns for the compound IDs, the SMILE strings for the compounds, and the average pKi values. We then use the predict from model file function I introduced in the beginning to load the pre-trained model from its tarball file and run predictions on compounds in the input data frame using the variables we defined. Since we're using the pre-featurized dataset, the isFeaturized parameter is set to true. This function will return a data frame containing the predictions. And now let's take a look at the most useful columns, which are the compound ID, the SMILE strings, the actual or true pKi value, the predicted pKi value that the model produced, and the standard deviation of those values. For example, for this first compound, the true pKi value is around 6.69, whereas the predicted value is 7.66. The standard deviation of around 1.33 here quantifies the uncertainty in the prediction, and such information is stored for the rest of the compounds in the test set. Now, to evaluate the performance of the model, we calculate the R-squared value, which represents how much of the variance in the data is able to be explained by the model. This code extracts the actual pKi values and the predicted pKi values from the pred-df data frame and calculates the R-squared score between these values, rounding the output to 6 decimal places. From the performance table for this model that we displayed in tutorial 3, the best valid R-squared score, or expected test R-squared score, was 0.418125. And this matches the calculated R-squared that we just found here. This means that the model's performance is consistent with what was expected from tutorial 3, and that the model is able to explain around 41.8% of the variance in the actual PKI values based on its input features. Lastly, we can visualize these results in a scatter plot of predicted values versus actual values. We first import perf plots, which is a plotting function, and then we'll use the second function introduced at the beginning, plot_pred versus actual from df, in order to show how the predicted and actual PKI values compared using the information stored in the pred_df data frame. So now we can see how the model performed visually. We can see that the points are spread somewhat close to the 45-degree line, but there is still some variability and a few outliers. The model performs moderately well, but there are still areas in which it could improve, which could be accomplished through later steps like hyperparameter tuning. And now we've applied a trained model to generate predictions on a new set of compounds and evaluated the performance of the model using the R-squared score, and then visualized this using a scatter plot. In the next tutorial, we'll move on to optimizing model hyperparameters. Thank you so much for watching.